Hello, this and my other YouTube videos are extracted from the History of Man series, currently 6 books published in print, ebook, and most importantly, audiobook. I'm a storyteller, and if you like these video stories, you'll love the History of Man series audiobooks. Great for commuting or just sitting back and relaxing. And unlike a novel you've read where you know the ending, you can listen to these books on tape more than once. There's so much to learn. Available on Amazon and audible.com, I narrate the audiobooks. And the best part about that is you can listen to these stories without having to look at my stupid face. And with that said, let's get the show on the road. Hello, this is John Bershoff with another episode of History of Man series. Today's subject, Global Warming 101, Part 3. To understand global warming and its ugly stepsister, abnormal global warming, scientists need to construct ancient temperature timelines. As mentioned in another video, Neanderthals didn't exactly record temperatures for us, nor did T-Rex. The first point in history where direct measurements of global climate data from multiple spots, especially average world temperature, traces to 1880, when enough data points from around the globe were obtained. Prior to that, global temperatures going back in history require science. Paleoclimatology is the study of climate change over the entire history of our planet. The materials used to help reconstruct ancient temperature timelines are termed proxy materials, such as ice, bone, rocks, fossils, coral rings, and so on. These proxy materials leave telltale signs of the ambient temperature when they formed. But first, the proxy material needs to be dated. It needs to be date stamped. Radiocarbon and other radiometric dating are used to date stamp the proxy material, which is then analyzed for what the average global temperature was or had to be at the point of that proxy material's creation. Now, the first and most famous is carbon-14, dating. Carbon-12 is normal carbon, 6 protons and 6 neutrons in the nucleus and 6 electrons in orbital stations around the nucleus. So here's your carbon-12. You got 6 protons, 6 neutrons in the nucleus, and 6 electrons in orbital stations around the nucleus. By the way, the atomic number of an element equals the number of protons or electrons, since they must be equal. So the atomic number is the number of protons of an element, and the atomic mass is the mass of the protons plus the neutrons. Atomic mass, protons plus neutrons. You know, I guess the electrons are not part of the atomic mass. They do have near equal mass to protons and neutrons, but maybe they're too busy zipping about to be part of the atom's mass. Electrons, though, are irrelevant for dating. Well, unless the girl or the boy is electrifying and comes into your orbit, then you want to date. It is the neutrons that are important to us. As an aside, you maybe have heard of Heisenberg's uncertainty principle, maybe from the Big Bang Theory, the sitcom. You can know where a subatomic particle is, like a photon or an electron, or how fast it is moving, but you can't know both simultaneously, where it is or its velocity, because measuring one alters the other. Now, this is perhaps true with a boy-girl relationship. You can possibly know where the relationship is or how fast it is heading in a certain direction, but if he's smart, he dare not ask her both. Anyway, as another aside, you most likely have heard of Schrodinger's cat in the box with a poison vial that opens at a random point in time. Is the cat alive or dead? This cat in the box sounds like a Dr. Seuss children's book. But anyway, this cat in the box is the kindred thought experiment of Heisenberg's uncertainty principle. It is about what is called quantum superposition, where a quantum state can be in two positions simultaneously, yet can't be proven because measuring one alters the other. What am I talking about? Well, take that electron mishigas I just mentioned. Electrons can have two different velocities simultaneously, or superpositions. Or it can be in two different orbital shells simultaneously, or superpositions. The point is, you don't have to prove it. You don't have to open the box to know where the electron is or how fast it is moving. That is, you don't need to know if the cat is alive or dead to mathematically prove quantum superpositions do in fact exist. You can assume that the two superpositions do exist, just like you can assume the cat is both alive or dead without opening the box. Just because as puny humans with our limited investigative tools cannot prove quantum superpositions, at least at this point in time, doesn't mean they don't exist. That is sort of what Schrodinger meant by his alive or dead cat in the box, the Dr. Seuss thought experiment box. Of course, a cat poisoned to death in a box would not make a very good Dr. Seuss bedtime story for your bratty 2-year-old. But anyway, returning to radiometric dating, Earth also has isotopes of carbon-12. Isotope is an extra neutrons in the nucleus. It has carbon-13 with 7 neutrons in the nucleus, and our baby, carbon-14 with 8 neutrons in the nucleus. So here's your carbon-14, 6 protons, 8 neutrons in the nucleus, and 6 electrons in orbital shells around it. Now, for any given element, the number of protons and electrons does not ever change. They have to equal and they never change. The neutrons are what we're interested in. If you add a proton, not a neutron, but a proton to the nucleus of carbon, it is no longer carbon. It is nitrogen. And in all atoms, the number of protons always matches the number of electrons. It is the neutrons that takes a stable element and makes it unstable. Now, protons determine the identity of an atom. You know, the chemical properties, the size of the atom, so where it can fit into a chemical bond. And also, protons especially determine the number of electrons since they have to match. It is the electrons that determine the atom's personality, its flavor, its ability to actually form those chemical bonds. What do neutrons do then? Besides take up space, they keep protons from killing each other. Carbon-12 is 99% of Earth's carbon. Carbon-13 is about 1%, and our baby, carbon-14, not much at all, a fraction of 1%. How does carbon-14 even form? Well, solar heat drives extra neutrons into carbon-12 and other naturally occurring radioactive elements. Now, there ain't room there in the nucleus, so the nucleus becomes unstable, and for carbon-14 especially, it wants to jettison that extra neutron. So here's your carbon-14. It has 2 extra neutrons. It doesn't like it. It wants to kick out that extra neutron. It ejects 1 neutron as what's called beta decay radioactivity at an exact pace, rhythmic, with a half-life of 5,700 years. So it kicks out that neutron as beta decay, which actually is a high-energy electron, also called a positron. So the neutron actually becomes a positron plus the release of energy. That is accurate. The half-life, 5,700 years. Now, most carbon-14 is in the atmosphere, and when stuff is made, like a Neanderthal bone or a plant, the carbon in the matrix by the photosynthesis equation, carbon dioxide plus water equals the carbohydrate backbone plus oxygen. So here's your photosynthesis, and carbon dioxide, and some of that carbon could be carbon 14 plus water gives you the carbohydrate backbone of carbon, hydrogen, oxygen, which then gets inserted into bone and plants and whatever. And some of that carbon is carbon 14. Now, this reflects the atmosphere when it was made. So that bone, its amount of carbon 14 reflects what the carbon 14 was in the atmosphere at the time it was made. Depending on how much radioactivity is left is a measure of the half-life. Radiocarbon dating using carbon 14 is accurate for 10 half-lives or 57,000 years. That is the accuracy of carbon 14 dating. So how do paleoclimatologists go beyond 57,000 years? They can't very well use carbon 14. That's a good question. Well, there are other radiometric dating isotopes. Uranium-235, for example, with 92 protons, 143 neutrons. It needs a lot of neutrons to keep those protons from annihilating each other. And it decays to protactinium-231 with 91 protons, 140 neutrons with a half-life of 34,300 years. So here's your uranium-235. It has 92 protons, 143 neutrons, keeping those protons from killing each other, and 92 electrons. When it decays, its half-life of 34,300 years, it decays to protactinium-231 with 91 protons, 140 neutrons, and 91 electrons. So whereas carbon-14 decays to carbon-12, it still stays carbon, uranium-235 actually loses not only a neutrons, but it loses one proton, so it becomes a different element, protactinium. You could use, besides uranium-235, you can use uranium-238. Its half-life is 4.5 billion years. That's its half-life. So that takes you to the age of our planet. Potassium-40 decays to argon-40. Potassium-40 to argon-40, its half-life is 1.3 billion years. You can go back, several billion years using potassium-40. But my favorite, although we can't use it, my personal favorite is zirconium-96. That decays to molybdenum-96 with a half-life of 20 quintillion years, which in a universe that is only 13.8 billion years old, there's zirconium, its half-life is 20 quintillion years. So in a universe that is only 13.8 billion years old, the first half-life of zirconium, its first half-life, is 14 billion times the age of the universe. If you happen to stumble upon any zirconium-96, it is primordial. It has probably not decayed at all. It came with the universe. Radiometric dating is science. It is proof. It is not faith. It knows no God higher than the immutable physical laws of the universe. Once a proximate material is date stamped, it is then analyzed for the ambient temperature when that material formed, which will be explored in the next segment of this series. Global Warming 101, Part 4. So I have 6 books out, History of Man series. This is the first History of Man series. There's the other 5, working on others. It's a style of writing called jumping off, where I have a baseline, which in my case is medicine and science, but I jump off into other things like astronomy and art and music and sports and philosophy and geology. I come back and then I jump off again and come back, jump off again. It's maybe not a style of writing for everybody, but I promise you with the turn of every page, you'll probably learn something. I certainly did. The books are available in print, e-Kindle, and of course, audiobook, where yours truly does the narrating. I hope you enjoyed this episode of History of Man series. Pick up the next one, the next part 4. And thank you very much for listening. Be well. Have a good day.